Easier, it's already ready. Okay. Yeah, let's get started. We're already a couple of minutes behind. So, right, my name is Venkat Guruswamy. I'm a senior scientist here at the Simons Institute, and it's my pleasure to welcome you all to the Simons Institute and this week's workshop. Just a few brief remarks about the Institute and the programming, and then I'll hand it over to the workshop. So as pretty much all of you know, the Simons Institute is the leading international venue for collaborative research in theory of computing and related fields. It was established in 2012 with a very generous grant from the Simons Foundation, who continue to support us generously. The Institute each semester brings together the world's leading researchers in theory of computing and related fields, as well as the next generation of outstanding young scholars in the form of junior fellows and visiting students and postdocs. And each semester, we have two programs that attract several long-term visitors, junior and senior, to Simons and Berkeley. And these programs also include multiple workshops, which convene more short-term visitors, as is happening this week. So this semester is a bit special because we have two programs with a lot of synergy between them. It was deliberately co-located that way, one on error-correcting codes and the other one on quantum algorithms, complexity, fault tolerance. And in fact, these programs shared their first workshop and as well as the boot camp and so on. And so this week is the final workshop of the error-correcting codes program, which is called, and the workshop is called Advances in the Theory of Error-Correcting Codes, basically to showcase advances on old classic problems in coding, as the organizers will introduce. And I want to thank the organizers for their work in putting together a nice program, including a break to watch the eclipse and things like that. So they are Swastik Koparty, Shivakant Gopi, and Mary Wooters. And Mary is also a co-organizer of the full program this semester. And a few logistics, and then I'll hand it over to Swastik. So we have food before the first talk and during the breaks just outside where you were before. For lunch, you're on your own, but there are many excellent choices walking distance. And I think the weather this week is going to be very good. And we ask that you please leave any food and drinks outside the auditorium. Water in a bottle is fine. Otherwise, please leave it outside. It helps us keep the auditorium clean. And if you need to leave your backpacks or other valuables, there are lockers on the other side when you go for lunch, etc. And we have as always, all our talks are live streamed and videographed. And Omiyad Far is here to help with any AV issues. And for those of you who might be active on social media, we invite you to consider live tweeting from the workshop. And if you do so, please tag us at Simons Institute, and we'll be sure to retweet your posts. It kind of helps those who couldn't be here to kind of follow along as well. And finally, a special round of thanks to our events team, which includes Ashley, Lida, Frida, and Francis for managing all the logistics. Definitely, these events would not happen smoothly without their dedicated hard work spanning a long time, including they're also on deck this week to help with any questions. So thanks again to the organizers, and thanks to the staff who make this happen. And with that, I'll hand it over to Swastik to introduce the workshop.
Okay, great. So I don't have much to say. Thank you so much for coming. We have a really great bunch of speakers coming to speak. And yes, and it's quite light. We have an eclipse, and so we'll have time for discussions. And yes, so the first speaker today is Shashank. He will be telling us about list decoding of standard codes.
Hey everyone, thanks for coming to the first talk. I'll be talking about some list decoding results for Tanner codes and other expander-based codes. Let's start with some basics of coding theory. A code is, let's say for now we are talking about binary alphabet. So code is a subset of 0, 1 to the n. Traditionally, code has been used for communication. So suppose we want to communicate k bits of information, then we could encode it into an element of this code C, say n length n string. And when this encoded string is passed through a noisy channel, some of the bits may flip and it changes to y tilde. And a code is supposed to be designed in a way that it is possible to recover y starting from y tilde. And this is the part that is called decoding, and this is the focus of this talk. Uh, so the code C is called linear if it is a subspace of f2 to the n, and two important parameters of a code are its distance and rate. The distance is minimum normalized Hamming distance between any two distinct code words, and the rate is ratio between k and n, which is a measure of how densely packed the code is. Pictorially, if this is the entire space 0, 1 to the n, the code words might look like a spread out subset of this set, where each pair of them is separated by at least delta n coordinates. If a particular code word y was corrupted in a small number of positions, say delta over 2, then we could at least theoretically hope to recover y starting from y tilde. But beyond delta over 2, these balls will start to intersect. And at that point, we have to rely on something called list decoding. So list decoding comes in when the number of errors exceed delta over 2, which is the unique decoding threshold. And the hope is that number of code words will be polynomial if not 1. If it becomes exponential, then it's hopeless to try and recover the list of code words. So the classical Johnson bound says that there is some threshold between delta over 2 and delta, such that up to j of delta number of errors, the list size is bounded. And the algorithmic task is to find this list. So in this talk, we'll be focused mostly on list decoding up to Johnson bound. So combinatorially, we already know that the list is bounded, and we want to find the list. Let's look at the code in question. So we work with Tanner codes. These are also called expander codes. Let's say we have a sparse bipartite expander. So we have n vertices on both sides. I call them L and R. The set of edges is E, and the degree on both sides is D. And it's a lambda expander in that the second largest singular value of the bi-adjacency matrix is bounded by lambda. So based on this growing family of expanders for which we do know of explicit constructions, we can define a family of code where code words are going to be assignments of 0, 1 assignments to edges. So each code word will look like some 0, 1 assignment to every edge, subject to some constraints. So what are the constraints on these code words? Every local view from any vertex should belong to some inner code C0. So each vertex on the left or the right will be seeing D edges incident on it. And we want those D bits to belong to some inner code. So for example, this vertex might see 4 edges and the bits written on them 0, 1, 0, 1. As long as this is in the code C0, this check is passed. And any assignment that passes all the 2n many checks is a valid code word. So this defines the entire code. And in this seminal work of Sipser and Spielman, they showed that if the inner code had normalized distance delta 0, then the global code also has a lower bounded distance in terms of delta 0. So generally, we consider lambda to be small compared to delta 0. We get roughly delta 0 square distance for a growing family of codes. Note that the degree is constant, so the inner code C0 is fixed. And we get a growing family of codes. These codes also have other nice properties, like they're low density parity check because each check is only concerned with D edges at a time. And they also have linear time decoders. Let's say a little bit more after about this later. Okay. So like I said before, we'll be focused on decoding landscape for the Tanner code. So let's say it's a binary code, so distance is at most 0.5. And so Sipser Spielman in their original paper had a decoder that could correct up to delta over 48 errors. This was improved in Zemore's bipartite construction with a particularly elegant algorithm to delta over 4. And using some generalized minimum distance decoding ideas, this was improved to delta over 2. But the progress has pretty much been stalled at delta over 2. And note that this is also the unique decoding threshold. Like I mentioned before, the Johnson bound says that for any code, not just this code, there is a threshold up to which we do know that the list size is bounded. And the question is, can we get an algorithm that works up to that threshold? So our main result is that we can have a polynomial time algorithm that list decodes up to this Johnson bound. So more formally, if the inner code has distance delta 0, the graph is a lambda expander, then up to the Johnson bound corresponding to this design distance of delta 0 minus lambda, we get a polynomial time algorithm that can list decode up to that threshold. Any questions about that?
For all of the previous unique decoding algorithms that you mentioned, linear time?
Yes. Yeah, so compared to that, this is like really bad running time.
So is delta really the distance of the code, or it's only a lower bound?
It's only a lower bound, so we don't know of better bounds on the distance.
Does anyone ever try to check it?
I don't know. So if you take this graph to be a complete bipartite graph, then this looks like tensor codes. So in that case, the distance is delta 0 square. So like there probably wouldn't be very general improvements to this, but it could be that with the degree it can be improved.
I think the concern is like if you take the graph to be random or
Right.
codes are random, then you can get to the G
Right.
bounds.
Right.
Certainly in some cases, but not explicitly.
Yeah.
What
can you
happens for super
clarify-
constant D?
Well, the dependence on D is pretty bad. So like anything super constant wouldn't give anything interesting, at least according to our results.
So regarding the question about delta, so your theorem holds for J of which delta?
The design delta.
The design.
Yes, only the lower bound. But this is also true for unique decoding algorithms, etc. Like you can only get to the half of the design distance. Otherwise, you can just prove a better distance of a lower bound. Okay, so going back to this picture, now we have a polynomial time algorithm that covers the entire range where we do know that the list is bounded. Why care about list decoding Tanner codes? Well, first, the progress on decoding these codes has been stuck for 20 years, so it does require some new ideas, and they also generalize to other codes, as we'll see. Broadly, there are two classes of code, some based on algebra, others based on expander graphs. And it seems like most list decoding algorithms that exist work for algebraic codes. So it's like Tanner codes have very little algebraic structure, so it's interesting to see what list decoding algorithms we can get for such codes. And Tanner codes, like I mentioned before, these are source of linear time decoders. So if we want to have linear time list decodable codes, say up to capacity, etc., it's good to understand the list decoding properties of these. And it, like right now, the running time is terrible, but probably it can be turned into linear time algorithm someday. What are the techniques we use? So first, we have this covering lemma, which is not a very radically different, but a new way of looking at Johnson bound, which is somewhat more algorithm friendly. Next, we use the proofs to algorithm paradigm for codes. Broadly speaking, it says that if the distance proof for the code is made up of local properties, like the inner code, and the local to global step is based on spectral expansion, then we get a list decoding algorithm up to the Johnson bound corresponding to that distance. Like formally, this local properties plus spectral expansion is captured by degree of proof in a sum of squares system. But for now, we can just think of local plus spectral expansion. And this paradigm was already used for decoding Tashma's codes up to the Johnson bound by Richardson Roy. I think that will be the next talk. And so convex optimization based decoders have been used for LDPC codes before because there is a natural LP relaxation. But the way these decoders were used was you declared success only if the output was integral. Uh, but for list decoding, we can't rely on integrality uh, if we want to find a cover for the entire list. So we use rounding algorithms, and we show that if we use the right rounding algorithms, then we can cover the entire list just from a single shot convex optimization. Uh, so let me tell you what the covering lemma is. It can be used to give a proof of Johnson bound uh, for arbitrary codes. There's nothing specific about Tanner codes here. If you're hoping for this, we'll have to wait for an hour. This is the real covering lemma. So we are given a family F of unit vectors in Rn and another unit vector G, such that G has large inner product with each of these vectors in the family F. So the inner product between G and F is greater than alpha. Think of alpha as some number between 0 and 1. So the covering lemma says that we can replace G by another G prime with a similar covering property with some loss, but gaining some structure. So there exists a G prime, which also has this covering property, but G prime has the additional property that it belongs to the convex hull of these code words, these family F. And it's just a geometric statement. There's nothing about codes here. So if this was the family F and this is the vector G, then there is a G prime, which also has large inner product with F1, F2, F3, but it lives in this convex hull. And the proof is just to take this G prime to be the smallest L2 norm vector in the convex hull. It must have the property that it has large inner product with all of the family F, because otherwise we would take the violating vector and find another, take a convex combination with the violating vector and find something with a lower L2 norm.
Can you say that again?
So if the smallest L2 norm vector did not have this property, then you can take the violating F and take a new convex combination, replace G prime by G double prime, which has a lower L2 norm. You can use the violating condition to guarantee that.
Where did G,
Sorry?
where did G play a role in that?
So it's implicit, like the convex hull is lower bounded in L2 norm because it has G coming in. So without that, it's hopeless. And that's pretty much all we need. We'll use this lemma to prove the Johnson bound next. First, we embed these code words into Rn to be able to use this. So this is a standard thing that we embed any string in F2 to the end to Rn by mapping zeros to ones and ones to minus ones. And then Hamming distance can be captured as the inner product. And these are all normalized, and the inner product is normalized as well. So if the Hamming distance between two strings is 1 minus beta over 2, that corresponds to inner product being beta. Hamming distances corresponds to inner products, and Hamming balls correspond to half spaces. And Johnson bound, I had not until now explicitly said what it was. So it says if the distance is 1 minus beta over 2, then the corresponding Johnson bound is 1 minus square root beta over 2. And it's a short exercise to see that it is indeed between delta over 2 and delta. Let's try to prove the Johnson bound using this. So remember, we made these embeddings, and if the distance is 1 minus beta over 2, Johnson bound is 1 minus square root beta over 2. What we know, let's say R is a received word. and again, we are working with any arbitrary code. Let's say R is a received word. Then for any H that is in the list, it must hold that the inner product corresponding to this R and H is large. Like their Hamming distance is small, which means inner product is large. And this is a fit case for the covering lemma to come in because there's a single vector chi of R, which has large inner product with all of these chi H. So there is some R prime such that, again, for any code word in the list, R prime has large inner product. There is a bit of loss. We went from square root beta to beta. But this R prime is in the convex hull of actually the embeddings of the code words. So if we think of it as a convex combination, we can find some distribution over the code, actually over just the list, but in particular over the code, such that on average, this distribution is close to H. And because the inner product is corresponding to beta, when we go back to the distance world, it's actually just delta. Like Johnson bound is chosen in this way. And at this point, so there is a distribution over code words that is less than delta distance. So H better be one of these support things in the distribution. Otherwise, for everything in the support, the distance is greater than equal to delta. So I can say this for any code word, and in particular, the entire list is contained in this support. And we can always pick a distribution D with support at most n+1 by the Carathéodory theorem, because we are working in n dimensions. So Carathéodory theorem says that if you're working in d dimensions, there's a convex hull of n points. We can always write anything in the convex hull as a convex combination of at most d+1 points. So this basically proves the Johnson bound for arbitrary codes. But this gives us an algorithmic way to find this list if we can do this L2 norm minimization, etc. But that for general codes is a bit hopeless to try because this step is going to take exponential time. We expect it to take exponential time for arbitrary codes. But for specific codes, can we do this faster? Or can we use relaxations that will allow us to do this faster? No, so the usual proof actually gives you precisely n. I don't know how to get rid of this +1.
You can actually. It's on your shortest point is on a face of the convex polytope. So it's one dimension lower. It's not an n dimension. It's an n-1 dimension. So immediately your proof gives you.
Oh, okay. So based on this, we can at least have an exponential time algorithm. And I'll say this because later on the polynomial time algorithm will follow this outline. Of course, there's a very roundabout way of giving an exponential time algorithm. You could just try all the code words. But so first we use the covering lemma to find a distribution such that it has this property for every H in the list. It is on average close to every code word in the list. We sample from this distribution. And if you use the Slack version where we are J of delta minus epsilon, then you can even see, using the distance of code, that H prime will be H with some probability. So now the plan is that, okay, first step takes exponential time. Can we use some relaxation of the set of distributions over code words that can do it faster, for which we can do step 1 faster? But then, of course, problem will be with step 3, where you need distance of code. So we need some relaxation that supports faster algorithms, but still has distance-like properties. And so for that, let's look at the distance proof of Tanner code, and we'll see where we need these properties. Okay, so let's look at the distance proof of Tanner code. And so let's take any two code words f and g. These again are assignments to f2 assignments to the set of edges, and let f be the set of edges where they differ, s be the set of left vertices where they differ, and t be the set of right vertices where they differ. And based on these, you can define like four distances. Uh, the edge distance is just how many edges they differ on. This is the usual distance between these code words. But I can also define a left distance, which is how many left vertices they differ on. And also a right distance, how many right vertices they differ on. And the fourth one is slightly artificial. It's just the geometric mean of L and R.
So S is the set of which is there's some difference.
Yes. If they differ in even one of those left vertex neighborhood, we count that.
Is the latter a distance, like a distance metric? Is it distance?
I'll have to check. Yeah. Just using distance very broadly. Yeah. So these are the distances. And so what we know is that if for everything where there's a difference in f and g on the left neighborhood, they must contribute at least delta 0 d different edges there because of the distance of the inner code. So if f and g differ on some left vertex, they differ actually in delta 0 d edges. That's the whole point of having a distance in the inner code. And like what that gives us is a lower bound in term lower bound on the edge distance in terms of left distance. And likewise, you can do the same argument for R and for the geometric mean. So we get some lower bound on the edge distance in terms of this LR distance. And we'll also prove an upper bound on this edge distance in terms of LR distance, and then comparing the two, we'll get the distance proof. This is the lower bound that we get. For the upper bound, note that the places where f and g differ must be contained in this set of edges between s and t, because s is the set where f and g differ on the left side. If an edge belongs to s complement, then it cannot differ between f and g, then they must be same. So instead of proving an upper bound on f, we prove an upper bound on this s and t, and it's an expander. So we use the expander mixing lemma, which bounds how many edges go between any set s and t in an expander. And just normalizing, we get an upper bound on the edge distance in terms of this LR distance. So we have a lower bound and we have an upper bound. We compare the two. And that will give us a quadratic equation, which is nice because until now we have not really distinguished between f and g being distinct. So getting a quadratic is nice because it allows for f and g being same. So the quadratic equation in terms of this LR distance is like delta LR minus delta 0 minus lambda times delta LR is greater than equal to 0. So it's possible that f and g are same. In that case, delta LR is just 0. So it's either 0 or it is greater than equal to delta 0 minus lambda. And the true distance is actually delta E. So you can use delta LR lower bound to conclude delta E, but this is only in one of the cases. So either f equal to g, or if they are distinct, they are quite far. So this is the entire proof of Tanner codes. And let's try to see what relaxation we can use, and I'll try to motivate using the distance proof where we need, what relaxation we need. So the continuous relaxation that we work with is, previously we had these assignments and everything, and the checks were all based on vertices. So let's say we use, instead of seeing a point distribution on every vertex, we allow some distribution, but still only supported on the inner code C0. So this vertex previously had a fixed code word of C0. Now it has 3 code words, still all of them being in C0 and with different weights. And these will induce different marginals on the edges. Likewise, this vertex might have a distribution supported on 2 code words. And again, it will have marginals. So the relaxation that we will work with will be an ensemble of distributions, n on left side, n on right side, with marginals being consistent between from the left side and the right side. So recall, like when we had point distribution, you can phrase the entire Tanner code as assignments to left side, right side with consistency along edges. It's the same thing, but with only marginal consistency. We get these ensemble of distributions, one for each left vertex, one for each right vertex, and consistency along edges. So this was already the relaxation that was used in LP decoding of expander codes. So we just asked for the nearest thing that this LP would give, and if it was integral, it would be the code word. But sometimes it would return fractional, like if the error was large enough, then we have no way of controlling whether this gives a fractional output or not. So we use a strengthening of this relaxation based on sum of square pseudo distributions, and I'll mention what those strengthenings are. But it should be clear that this is first of all a relaxation of the set of code words. It's actually also a relaxation of the set of distributions over code words, because each distribution will induce such local, each true distribution over code words will induce these local marginal distributions. But vice versa is not true. We can have local distributions that do not correspond to global distribution. So in a way, it's a set of, it's a relaxation of the convex hull of code words. But the nice thing is that we can hope for faster algorithms here. This entire thing we call a pseudocode word. Let's try to go back to distance proof and see where we need to modify things. The first part where we were having a lower bound on edge distance in terms of LR distance, that pretty much still goes through. So if I'm measuring distance from the 0 code word of a pseudo code word, you can verify that those things are still reasonable, because I'm ensuring that each of these local distributions are only supported on the inner code words. So we might have to modify these distances accordingly, but it still makes sense. Yeah.
You're now defining a distance on pseudocode words?
I'm trying to measure distance of a pseudocode word from, let's say, a true integral code word. Let's say just 0. So I'll have to modify the definitions accordingly. And instead of just counting whether something is different or not, now I have to look at the weight of non-zero code words.
Okay.
Or the weight of an edge being non-zero. And all of these weights are consistent because of marginal consistency. So we can use any distribution to do this.
And the condition of the pseudocode word is that it's a convex combination of code words that none of which are the 0 code word.
No. So like for the edge distance, we just look at, so the edge will have its own marginal distribution, only on 0 and 1. So we just count the weight of 1 there.
Weight means weighted with probability.
Yes. So yeah, so these are actually conditional random variables, like one whether FL is 0 or not. So we just count the weight of all non-zero code words here. So this inequality still holds true. It's the analog of F being a subset of S cross T.
Yeah, sorry, just one more clarifying question. So a pseudocode word I should think of like a labeling of real numbers to edges as being a legitimate pseudocode word if there exists small lists, or like if there exist distributions with small support that I can put on every single vertex,
Right.
so that the marginals for both sides line up.
Yes.
Okay.
Yeah. Or you can think of the pseudocode word as the set of distributions themselves.
Okay.
And from there you can infer the margins.
Got it. Thank you.
Is there, you mentioned small, is there a bound on, is it any, should the support be small for these pseudo distributions?
No, the local ones can have at most C0, like the inner code number of code words.
Okay, thanks.
Yeah.
So the right hand side here has degree equal to delta or something. The indicator for the FL is not 0. That's
Yes, that's for the entire neighborhood. So FL.
Left hand side is linear and right hand side is degree delta or something.
Yes. Yeah. But it's still, so this L tilde R notation means that I'm only looking at edges. If this just follows from this indicator inequality, you can remove all expectations, and just as indicator random variables, this inequality is true. But the next step that we had corresponded to something like expander mixing lemma, where we moved from the measure on edges to the complete measure. And this part is not true, not clear for these pseudocode words. And this question is even interesting for true distributions. But for true distributions, it holds because of some positive semidefiniteness properties of the moment matrix.
Sorry, so I understand you're trying to run through the proof you had before and see what's going on. But before we do that, can you say, what do you expect? I mean, if you had like probability 99.9 on 0 and probability tiny on something else,
Right.
what distance does that have from 0?
Exactly. Like for convex sets, we do not expect distances. So somewhere.
What are we expecting to happen here?
That's why we'll see exactly where things will break down.
You want to be close to the received word, right? So that won't be optimal. If there's some word you're trying to decode. So what you're saying will be optimal if that word is very close to 0, but otherwise.
Okay, but so for true distributions, this holds true based on some global matrix being positive semi-definite. And because that's still a convex constraint, we just impose that on our this local ensemble of distributions. The second one is also interesting because this, for integral cases, this is just trivial. When there's no E tilde, then it's just product of indicators. But for distributions, this starts to create problems. And this is where we have to have the set to be somewhat non-convex, because otherwise there's no point looking for distance proofs. So the strengthenings that we use for the pseudocode word are both motivated by these two inequalities. So we had this pseudocode word definition. The modifications, one, we use the positive semi-definiteness of PSDness of global covariance matrix. And the second one is that we assume that these are actually induced by even larger ensemble of distributions over T size sets, where T is much larger than D, but still constant. So this second condition allows us to have some non-convexity properties, which allows us to break. Let me show you. So the key steps, when we want to move from this expectation over edges to all pairs, of course we have to pay lambda, but this can be done using the PSDness condition. And then the second step, here x and y are some arbitrary functions, let's say. The second step, where we break this one E tilde into a product of E tildes, that's a non-convex condition. And for there, we use some low average correlation obtained by random conditioning. And this is almost a standard way of rounding sum of squares relaxations by now. So the second step is also responsible for these bad dependence on D, etc. in the exponent.
Sorry, I missed it. What are X and Y?
Sorry?
Capital X and capital Y?
Some arbitrary functions, as long as they are local.
Okay,
So, I'm sorry, but I'm not sure I don't follow. You added some more constraints that would remove the example that I gave, or?
Yes, because like in general, when we take convex combination, like you said, I can't prove a distance between 0 and something that has 99% 0. But this random conditioning will give me a set that is non-convex. Like the property that I will derive out of this random conditioning will be non-convex. And after that, I can prove that either everything is epsilon close to 0 or delta minus epsilon far from 0.
Okay, what's the random conditioning?
So let's see. I can tell you that after this. Like,
Sorry, okay.
yeah. Okay. Before we wrap this up, like so, the exponential time algorithm was we use the covering lemma to find a distribution and then sample based on this distribution and use the distance. We wanted an analog of this with polynomial time. The sampling part, let me write it as conditioning on all n coordinates. That's equivalent to sampling. Anytime you sample from a distribution, you can condition on it one by one. And the distance is essentially this quadratic inequality. So the polynomial time algorithm that we have, we use the covering lemma again with this L2 norm minimization kind of ideas to find a pseudo code word that has low distance from each of the list code word. But previously, when we were sampling, instead of that, we condition on some 1 over eta square coordinates. So sampling, just like from true distributions, we can get to integral code words. And after that, you can use all non-convex arguments. Likewise, after conditioning on 1 over eta square coordinates, we get some average low correlation property. And based on the proof that like the whole entire point of having those strengthenings of the relaxation was to be able to prove a statement like this quadratic inequality. Still quadratic, but with some eta error. So we won't be able to say that it's exactly 0 like in the integral case, that h prime has to be h, but it's some order eta close to h. And after that, we can just unique decode. So we do need some unique decoding properties from an arbitrarily small radius. But the first step took exponential time in the exponential time case, but here we can do it in n to the 1 over eta square time.
This is because the conditioning requires degree 1 over eta squared?
Yes, exactly. Yeah. The extensions, a very similar argument also holds for AEL amplification. So AEL amplification is, we start from some high rate positive distance code, and using AEL we can amplify the distance to almost close to MDS like parameters. So distance is 1 minus r minus gamma and rate is r, and the alphabet is some large constant. And using this, we can list decode these AEL codes up to the Johnson bound of this 1 minus r minus gamma, assuming only unique decodability of the base code. So if you rely on list recovery, etc., there were already algorithms to do this. But even if C base is like barely uniquely decodable, we can get some algorithmic result for the final code. And other extensions there for larger alphabet, again, you just change the embedding we did in the initial step, and that's all. Like the distance proof, etc., stays the same. And similar with list recovery or weighted list recovery, etc. We just need to change those embeddings initially. And even after we concatenate this AEL code, we can get to the true Johnson bound of the concatenated code, which is difficult with Reed-Solomon kind of things because you rely on list recovery. So the parameters are not as sharp. Here you just adapt the distance proof directly for the concatenated code. For future directions, like of course we want faster algorithms. The running time of these algorithms is quite poor because of this 1 over eta square kind of dependence. And there are examples in the past where SOS has been replaced by faster algorithms. And because we algorithmize this proof of Johnson bound, in general we know of codes that are tied for Johnson bound, so we don't expect improvement directly to the covering lemma. But for specific codes, can we use better covering to guarantee better list sizes beyond Johnson bound? And what happens for quantum LDPC codes or quantum analogs of these expander codes, etc. We have some upcoming work that says that we can list decode quantum analog of this AEL amplification.
Question. So for going beyond the Johnson bound, is there what kind of statement is, if there's a certain style of proof for going beyond Johnson bound, then would this automatically?
Yeah, we don't know. Like it seems like even to have candidate codes for that, it's not clear. Yeah, like some natural things would be like for Reed Solomon, you interleave, look at interleaved Reed Solomon, etc., and then try to impose conditions. Can you do something like that with AEL, for example? And would that allow some better list decoding?
I see. We don't have non-algebraic examples. We don't have combinatorial examples where you go beyond Johnson.
I mean, we do, but then the proof technique is very different. Like then there is a lot more structure, like random codes, etc. But like I don't know of a lot of examples where you smoothly extend Johnson bound, and that's the kind of statement that we would want here. Like something holds for every code, and then when there's this extra property, we can go beyond Johnson bound.
Other questions? Okay, great. Thanks. Great.